Welcome students. Uh, in BSc we have studied a lot of ordinary differential equation, how to solve a linear ordinary differential equation, different kinds of ordinary differential equations. By solving a differential equation, by getting the solution, we can draw the picture of the solution. But here now I am trying to show you that without solving a differential equation, we can visualize the solution picture, or you can visualize the picture space. That space is called the phase diagram. After BSc, I think you have studied phase diagram. You have studied phase diagram in MSc. So the title I have considered today: elegance of phase diagram. Elegance of phase diagram. How a phase diagram visualize a solution of particular ordinary differential equation. We can, by seeing the solution space, we can have a clear concept of the concerned differential equation. Now let me consider one very simple ordinary differential equation. I am writing very simple now, starting with very simple ordinary differential equation. Dy dt is equal to 1 minus y. So this is dy dt is equal to 1 minus y. This is first order linear differential equation. Easily we can solve it in a very simple way. We have learned in BSc. But now I don't want to solve this equation. Without solving this equation, I want to visualize the solution space. Now what we do next step, if we do dy dt is equal to 0, that gives 1 minus y is equal to 0, that gives y is equal to 1. This y is equal to 1, this curve y is equal to 1 is called critical point or equilibrium point. Now we try to draw a picture. Now try to draw a picture like this. So our differential equation is dy dt is equal to 1 minus y. So by equating 0, dy dt is equal to 0, we are getting 1 minus y is equal to 0, y is equal to 1. This is called equilibrium point, critical point, or this leads to steady state solution. So y is equal to 1. If I consider this axis as t, and this axis as y, so y is equal to 1. Y is equal to 1 means this line. This line is y is equal to 1. This is origin. Now see our this is our differential equation. Okay, now how to draw the solution space. See, dy dt is the slope. Dy dt always gives the slope to the solution curve, to the constant solution curve. Dy dt gives the slope to the constant solution curve. For different value of y, we get slope at different position to the solution curve. Now we draw the solution. Now we draw the slope curve. So when y is equal to 1, dy dt is equal to 0. So this line, so this is dy dt is equal to 0, means slope is 0. So the direction of the slope will be like this, and this line is called steady state solution of the differential equation dy dt is equal to 1 minus y. Now see, dy dt, we have dy dt is equal to 1 minus y. Now if I put here dy y is equal to 2, if I put here, that is, if we consider this line y is equal to 2, if we consider this line y is equal to 2, we see, if we consider the y is equal to 2, so our differential equation is dy dt is equal to 1 minus y. It is our differential equation. So if we consider y is equal to 2, so we get dy dt is equal to 1 minus 2 is equal to minus 1. So the how will be the slope at any point on this line will be like this. Dy dt is equal to minus 1, negative slope, means like this, tan 45 degree, tan minus 45 degree, like this. Now see, if I consider y is equal to 1, if I consider y equal to 0 in this differential, in our differential equation, we get dy dt is equal to 1. So slope is 45. Slope is 45 degree slope, means on this line slope will be 45. So like this, slope will be. So this differential equation has only one steady state, that is y is equal to 1. This differential equation has only one steady state solution, that is y is equal to 1. Now see the behavior of the solution around this y is equal to 1. To visualize the behavior, we are considering the slope field. Now consider any point y is equal to half. Now we investigate whether this steady state is stable or unstable. Whether this steady state is stable or unstable. So take any point close to this line y is equal to 1. So consider another line y is equal to half. Now if I consider y is equal to if I put y is equal to half here, so then dy dt is equal to 1 minus half is equal to half. 1 minus 1 by 2 is equal to 1 by 2. So slope in this region, so the picture of the solution, slope of the slope to the solution curve will be like this. If I consider a point in this area, so that slope will be, you can verify like this. Always it approaches to the steady state. Always it approaches to the steady state like this. Like this. Now in upper, this upper from 1 to 2, we consider a point here. We now investigate this region. We now investigate this region. What will be the slope of field? Take a point 3 by 2. Then dy dt is equal to 1 minus 3 by 2 is equal to minus half. So the arrow will be like this. So this from upper side, if we take any point from any of this region, suppose this, if we stand here, we always move towards the steady state solution. If we stand here, always we move towards steady state solution. So within the region y is equal to 2, so y is equal to 0 to y is equal to 2, if we stand any point, so always we move towards the steady state. Always we move towards the steady state solution. So this steady state is stable. This steady state is stable. If it would happen that we consider a point here and we move away from the steady state, if we move away from the steady state, then the steady state we can call it the unstable steady state solution, unstable. But if stand here, if one particle stand here, always that particle moves towards the steady state, solution. So this, if I draw another curve, fresh picture, if I draw a fresh picture, that is t, that is y, that is steady state, y is equal to 1. This is the steady state solution. Now this is y is equal to 2. Now if we consider a point here, steady state solution, direction is, if we stand here, so always we move towards the steady state. If we stand here, always we move towards the steady state. So picture will be like this. Slope field will be like this, and so thus this steady state is stable. Stable steady state. Stable solution. Stable solution. Now see how beautiful picture is, the elegancy of the phase space. This called also phase space. Phase space or phase portrait or phase diagram. See the elegance elegancy of the phase. Without solving a differential equation, we can visualize the solution, nature of the solution, or the solution picture, how will be the solution space. So ultimately, so the solution, the picture of the solution will be like this for different. Also, you cross check this picture by solving the differential equation in a very simple way, what we have learned in BSc. So like this. So y is equal to 1 is the steady state solution. Now this we have seen in this region y is equal to 0 to y is equal to 2. What will happen outside this region? Now draw another picture. Let me draw another picture. So this is t and this is y, and this is y is equal to 1, that is steady state solution. And we know from within this region y is equal to 0 to y is equal to 2, the solution is stable. If we take any point, it moves towards the steady state. The steady state is stable. Now we consider the outside region. What will happen in this region if we now consider the lower part, negative part of the y-axis. So dy dt, we have dy dt is equal to 1 minus y. So we consider here y is equal to minus 1. So dy dt is equal to, if I put y is equal to minus 1, that will be 2, positive 2. That is, so the slope field will be like this. Okay, now if I consider y is equal to 3, y is equal to minus 2, if I consider here y is equal to minus 2, so dy dt is equal to, here y is equal to minus 2, so dy dt is equal to 3. The slope will be slightly upward than the previous one. And like this we can go up to infinity. Y is equal to minus 2, y is equal to minus 3, y is equal to minus 4, y is equal to minus 5. Then we will get dy dt is equal to 3, dy dt is equal to 4. We can tend to dy dt is equal to infinity, means that is tan pi by 2. So like this, the solution in this region, like y is equal to, this will be slightly upwards than the previous one. So if we go to infinity, then the slope will be pi by 2. The angle of the slope will be pi by 2. The slope will be pi by 2. Now we consider, if we consider this region y is equal to minus half, y is equal to, if we consider y is equal to minus half, y is equal to minus half, then y is equal to, if we consider y is equal to minus half, consider y is equal to minus half, so dy dt is equal to 3 by 2, then slope slightly downwards than the lower part. So the picture of the differential equation will be in this region. Now I think this region, if we consider we stand here, we always move towards the steady state. Move towards the steady state. If we consider this, so we always move. So this will be like this. And now we consider the positive part, y is equal to 3. Y is equal to 3. Y is equal to 3 considered, then what we will have, 1 minus y is equal to 3, dy dt is equal to 1 minus 3 is equal to minus 2. So minus 2. So minus 2 means then the picture of the slope field will be like this. Picture of the slope field is like this. This is also moving towards the steady state solution, that is y is equal to 1. This is also moving towards the steady state solution. At this point 2.5, this point is also move steady state solution. So in this region also, so the steady state, which one is steady state? This is the steady state solution, stable. Obviously we have checked that this is stable steady state solution. So if we stand here, we always move towards the steady state. If I stand here, always we move towards the steady state solution. So see the elegance of the phase space. This is called the phase space or phase diagram Elegance, how the beautiful picture. So without solving a differential equation, we can visualize the picture of the solution. And or the nature of the solution we can easily visualize, and through this phase space we can see the excellent picture. We can get a clear idea about the solution of the concerned differential equation. Now here we have considered a very simple case, but also this differential equation may be linear. This is independent of t, but we can consider also this is dependent of this is, we can consider also this function also, maybe we can consider a function of y and t both. This we can we can change it by this way, and this maybe linear or non-linear. We can also consider this non-linear terms also we can consider. So the y is equal to 1 is the steady state, and this is stable. This is stable solution. Why this is stable? Because if I stand here, we always move towards the steady state. If I stand here, we always move towards the steady state solution. So the steady state, this steady state solution is stable. This steady state solution is stable steady state. Stable steady state. Steady state, equilibrium, or this is the equilibrium of the system of the of the considered differential equation. So next video we can consider we can consider a complicated nonlinear differential equation, and without solving we can show that we can show the nature of the solution or the picture of the solution. We can show easily, and this point is called the critical point, equilibrium point. There is a very important topic in BSc or MSc or in different kinds of GATE, NET, SLATE examination. This is very important topic. Often we have to check this stable or unstable. Here we see that this stable solution, this is stable steady state. This equilibrium point y is equal to 1 is stable solution. Thank you.